Good evening. To understand how something works, it's often best to try to build it, or the nearest thing to it. This project is not for the faint-hearted. How to generate video patterns on a video or TV screen. So, sit back, put your seatbelts on for a new episode on the Technomora channel. Not too long ago, I was surfing on eBay, and just out of curiosity, I was having a look at what sort of prices TV pattern generators went for nowadays. And I have to say, the prices for the pattern generators were really rather crazy, I would say. Although I suspect it has to do, on the one hand, with them becoming scarcer and more people taking up on the hobby of electronics and more specifically restoration of stuff. So I thought, well, since I'm always very curious and I want to find out how stuff works, and one of those things is how an old style analog TV works, I thought, wouldn't it be nice if I could build a sort of a pattern generator for myself, and at the same time build something that might be useful for less fortunate hobbyists out there who would still like to restore a TV but really don't want to shell out, say, $150 or even more for a pattern generator and have fun building one at the same time. And what you're seeing right there is really the result of that long drawn out thinking I had not too long ago. Okay, granted, it doesn't look like much and it's still only on a breadboard, and admittedly it only generates a very simple pattern, but I think for some basic testing and for testing out TVs or monitors, this will do nicely. I mean, this is the pattern I'm getting now. Okay, so let me put the light. Okay, so the flashing you see on the screen, I mean that rolling black bar you see over there is is really the camera shutter speed not corresponding to the refresh rate of the screen. Okay, but actually that's the pattern that little device you see over there is generating right now. But I think I'm getting ahead of myself, so I better start at the beginning. Okay, so I drew a little schematic, really, or diagram I should say, of what kind of signal we will use to create an image. And there you have it. Now, just for my American viewers, the signal I'm going to describe and the signal the pattern generator generates is a PAL signal and not an NTSC. Although, technically speaking, the difference between a black and white PAL and a black and white NTSC-M signal are not that big, so with a little bit of tinkering I'm quite certain you can make the pattern generator I built work for an NTSC video monitor. In any case, the theory behind it is exactly the same. So long ago, some wise men, probably engineers, decided that an analog TV signal should look pretty much like what I drew here. So you have a sort of negative going square pulse, which goes after that into a staircase like signal. Okay, so I mean, this is theoretical, of course. The signal between this point and that point could be really anything. I mean, shape-wise. The only thing that's important is that the image is formed from 300 millivolts upwards to maximum 1000 millivolts. Now, this is what I measure in practice. In theory, people will always talk about a minus 300 sync signal and a plus 700 millivolts maximum, that is, for a white level signal. The black level being at a, relatively speaking, 0 point. Of course, it's now 0 when we measure this signal. In reality, black level is at plus 300 millivolts and white level is at a maximum of 1000 millivolts. Okay, but that's the way it's designated in theory. So minus 300 millivolts synchronization pulse and a maximum 700 millivolts positive white level video signal, and any value in between. Of course, those will create all sorts of gray values. Okay, so let's say, technically speaking, a 350 millivolts signal, or I should say a 650 millivolts in reality signal, will generate a grayish signal. So that's what you need to remember about this. Now, I know you might probably be interested in more technical details. If that is so, then I'm prepared to elaborate a little on the theory behind the signal. But for now, for this project, this is the only thing you really need to know. Namely, that you need a sync signal of 300 millivolts high, of not more than 4.7 microseconds long. Okay, and the image signal itself is 52 microseconds long. Okay, remember, we're talking microseconds, okay, not milliseconds. Right, now a whole image in PAL is built up out of 625 lines, and when they say lines, they literally mean a line that covers the screen from left to right. Okay, now to cover the whole screen with a PAL signal, you need 625 lines. Okay, and 625 lines create what they call a frame, and a frame is actually 1/25th of an image per second. You can see it here, I drew it. So one image in 1 second creates 25 frames per second, and 25 frames is 50 fields per second. I'll tell you in a minute what fields are. and you need 625 lines per frame to build 1/25 of an image, and a field is 312.5 lines. So why are we talking about field here? Well, an image is really built up from what they call interlaced lines. So the image is really built up by scanning 312.5 times a line over the screen, and that's what they call the even frame, and then the odd frame, and then they scan a second time, and they shift the next 312 lines one line down, so that the odd lines are scanned in between the even lines. Okay, so you build up an image effectively by first very quickly drawing 312 lines, and then starting from above again, and then shifting one line down, and then drawing very quickly another 312.5 lines. If you do that rapidly, very rapidly, you effectively draw 625 lines, one frame. Remember, one image in 1 second is equal to 25 frames, at least for a PAL signal. For NTSC, it's a completely different story. Well, let's say it's a slightly different story. No, it's a completely different story, but technically it's the same thing. Okay, trust me, it is. Anyway, we need to recreate a signal like this to be able to drive the image. On my scope, what you see there is the output of the line generator. And for your information, we will build all the signals we need with the help of 555 chips. Okay, so 555 oscillators. There are 3 of them on this breadboard, and I'll explain to you in a minute what each of those oscillators do. But basically what you see over there is a blank, or let's say a black image. Okay, so an image which is blank, which shows nothing, just an even field. And you see, when you look at the cursors, okay, so these 2 lines, and I match them up with the pulses, you see that the difference between the 2 lines is, according to my scope, 63.9 microseconds. Okay, so remember, a PAL signal is, or one line of a PAL signal is 64 microseconds. So let's say I'm pretty close to within tolerance of the 64 microseconds, and okay, I could switch on the monitor screen and show you what sort of image it would give, but you would see nothing. It would just be a flat uniform field. Okay, but the signal we need to generate really needs to fall in between, and I'll tell you exactly in between what. In between those 2 lines. Okay, in between those, actually no, it's like this, in between those 2 lines. In between those 2 lines, the signal needs to, and actually it's more like this. I'm struggling a bit here with my with my scope, but okay, there you go. So the image we will need to generate will need to be between these two lines here. Now suppose we would like to draw the symbol 1, a fat symbol 1 on the screen. How do you think that would be done with a signal? Suppose we only want to draw the upper part of the 1. How would we do that? By using lines. Well, we would take the first line of the 1, this upper line here, and draw it on line number 1. Then you see, if you go a little bit lower, you have one bit of line here and one bit of line there. So we draw a tiny little bit. Say this one is drawn in white, okay? So we draw a white dot here and a white dot there. And we go line by line, we go down over the screen, and every time we encounter a little bit of the symbol 1, we draw a white dot on that specific line, and we go line by line. After a while, you do start to see the image of a 1. Now, what does that mean signal wise? Okay, so what would you see on, say, an oscilloscope if you were watching these lines being drawn? Well, for the very first line, you have black, 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 white, 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 black, and black until the very end. Okay, so that means that your line starts here on your screen. That means that a pulse, a negative pulse of 300 millivolts is sent out, and then for a while nothing. So nothing more than this black signal here, which is 300 millivolts above the absolute zero, which is here. Okay, and then you have the start of this first line, this first white line here. Your signal goes up all the way to the maximum level it can output, which is, in our case, 1000 millivolts measured from absolute zero, or 700 millivolts measured from the blanking line. Okay, so the black level, which is at 300 millivolts higher, okay, than the absolute zero. And so you keep that signal up at 700 millivolts, and then you end the line here. Okay, so your voltage drops back to black all the way until the end of the line. Now if you go to line 2, you see we don't have a full line here anymore. We have part of a diagonal line and part of a vertical line. So you go down line 2, which is black, black, black. Suddenly you cut through the diagonal of the symbol 1, which is a white dot. So you draw a white dot, a white signal. You emit a white signal of maximum voltage. Remember, that's 1000 millivolts from the absolute zero level. Okay, you go on over line 2, black, 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 and again you cross the line of the symbol 1, white. The signal goes up to maximum level, which is again 1000 millivolts from the absolute 0 point, which is here. Okay, so in effect what you see is that if on line 2 you intersect the diagonal part of the symbol 1 and then a vertical part of the symbol 1, which are very tiny pixels, really, just dots on that specific line. You see on the signal 2 spikes, okay? Instead of one big fat rectangular signal, you see 2 very thin, very high signals, okay? And thus the 1 is built up line by line. Of course, now I'm telling you all this, and it takes me, relatively speaking, 20 seconds to tell you all this. In reality, there would have been already thousands of lines drawn over a screen. Okay, so this is really quick. Remember, just one signal line, which you see here, is sent out at a frequency of 15,000, say almost 15,700 hertz. Okay, so 15.7 kilohertz or thereabout. So this line is sent out very quickly, then this line is sent out very quickly, then this line, the next line is sent out, etc. Now technically what I'm saying here is not 100% correct. Actually what happens is, in reality, is that first line 1 is sent out, then line 3, then line 5, then line 7, etc. When 312 lines have been sent out, the image, the frame actually starts again, but at line 2. So line 2 is sent out, line 4, line 6, line 8, etc. That's why they call an image interlaced. Okay, I have a cup of tea, very hot, strong tea, and we're sitting comfortably, so I think I can try to explain to you what I sort of put together. Instead of working with 2 separate fields, what this design does is really generating 625 lines in sequence. Okay, there is no odd field or even field. There is no interlacing. It just spews out 625 lines per frame. Yes, call that cheating if you wish, but since we're not going to generate anything specific, well, I mean, not a specific image or anything like that, this design will do to generate a simple pattern. Therefore, you need what I call here a line generator, okay, with a sync pulse, and that is formed by a 555 integrated circuit. That's a tiny little chip. Let me see if I can show you one. Oh, okay, I have one handy. So an NE555 is something like this, okay, an 8-pin chip. Nothing special. Now the NE555 has a few advantages. First of all, it's simple to use, and a lot of people use this chip to make all sorts of timers. You know, stuff which needs timing. You know, like an egg cooker or a development timer. And that's what this chip is being used for quite often. Now it so happens that the 555 has a few interesting properties, and one of those is that it can generate all sorts of square waves with all sorts of duty cycles. So you'll remember, if you look at a square wave of a certain frequency, a square wave has an uptime and a downtime, okay? And the amount of uptime compared to the full length of the square wave is what they call the duty cycle. And in this design, the duty cycle is really very, very useful feature of the 555. I mean, the fact that you can set any kind of duty cycle. The other interesting property of the 555 is that it has a technical frequency limit of around 1 megahertz, which makes it extremely useful for us, since it has no trouble whatsoever generating the 15.6 and a bit kilohertz we will need to generate a line. Okay, so if this can handle 1 megahertz, it can certainly handle 15 kilohertz. And of course, if I didn't mention this before, it's also very cheap. That being said, what we have here in front of you is what people call an astable oscillator setup. Okay, so the 555 generates a constant flow of square wave signals, and this one here on the schematic is configured in such a way that we can fully set its duty cycle with these potentiometers here. So it generates a fixed frequency pulse of 15,625 Hertz, and we can set its profile, so its shape really, by these two potentiometers here. Let's say its duty cycle. Okay, that's the correct term to use. Right. Now, the 555 outputs its signal through its pin 3, which you see here. Okay, and that signal is diverted to two parts of the circuit. One part is diverted to the little amplifier, which actually I should say the attenuator, which will output a signal to whatever appliance we hook up to it. So in our case it's a small monitor. And the other part of the signal, or well, I should say the signal gets also diverted to the vertical frequency oscillator you see here, which is, as you might guess, also a 555. However, this 555 here is not what they call an astable oscillator, but a monostable oscillator. Okay, I'll explain myself. So through pin 3, the first NE555, which generates a line, outputs a sync signal. You remember, that's just a flat line with one very short negative going pulse. That negative going pulse we're going to use not only to output it to the monitor, but also to synchronize the vertical oscillator. Okay, so every time any 555 gets a negative pulse on its pin 2, so the pin right next to its output pin, it fires and generates a square wave. Now, a monostable configuration, like you see here, generates one pulse for a certain duration and then stops. So every time it gets a negative pulse on its pin 2, it generates a square wave, it outputs it on its pin 3, and it stops. And that's what it does, and nothing more. And as it so happens, as you remember, the line that we generate, the blank line, always starts with a negative pulse. Now, isn't that practical? Yeah, how nice things can turn out for us. So we can use that negative pulse to start the vertical generator or the vertical line generator. This will generate a very short pulse, as short as we like. In fact, we can make it an extremely quick, extremely short pulse, or a very long stretched out pulse. And remember, when you saw the schematic I showed you before, a few minutes before, the longer the pulse you send on a specific line, the longer the line will be, the visible line will be drawn, okay, over the screen. If you send out a very short pulse, you get a tiny pixel, say white pixel. If you send out a longer signal, you'll get a white line. And that's exactly what this 555 does. There is a little bit of a special thing here. I'll tell you about it in a minute between these two, but let's get on with it first. So now we have a line generator, a baseline generator, and we have something to draw lines with. But that only draws a line every single line, and that's it. Yeah, it draws it at the beginning of the line, at the middle, in the middle, or at the end. It doesn't matter, but that's the only thing it does. Now, suppose you want to draw something, I don't know, in the middle of the screen, let's say. Well, then we have a bit of a problem. Remember, I told you I cheated a bit, okay? So I'm drawing 625 lines, one after the other. If you generate a pulse precisely timed with every line you generate, you will draw that pulse on each and every line, okay? So you will say, if you draw a very short little white line with the vertical oscillator, you'll draw 625 times, one after the other, a little white line, which will create a vertical white line on your screen. But say we don't want a vertical line but a square. So how are we going to do that? Now I hear you thinking, what about switching on and off this vertical oscillator, okay, at a certain moment, so that it only starts to draw somewhere in the middle of the screen. It draws, say, for 50 lines, and then it switches off again. Ah, indeed, you need a horizontal, astable oscillator, and that's what this 555 does. So this 555 here gives power to this one, and you can set its frequency with a potentiometer. Okay, so this one in fact over here. So this one switches on and off, on and off, on and off at a certain frequency, which is slower than the generated line frequency. Okay, remember this is 15 and a bit kilohertz. This is a bit slower. In fact, its maximum frequency is around 9 kilohertz. Okay, but you can make it go slower if you wish. It has a reasonably wide frequency, say, band in which it can work. So say from, I'd say 200 hertz to up to 8 or 9 kilohertz. And with this, we switch on the vertical oscillator, the monostable oscillator, on and off at any time we like. So we can switch the drawing of a line on at any point in the screen. I mean, vertically speaking. I know this is confusing. You would say, listen, you're talking about a horizontal oscillator there, and you're telling us now it influences where the line is drawn vertically. Yes, that's true, but remember, this, okay, is what switches the vertical oscillator. Remember, it draws a line each line for 625 lines. Okay, this one I mean switches this one on only when it is needed. Okay, and it means that it switches it on for only a specific horizontal portion of the image. So that's why I call this the horizontal oscillator, not the vertical one. I know it's confusing, but bear with me, we're almost done. Now remember, I told you there's a little special thing in here, and which is this part here. Okay, it's a capacitor and a potentiometer. Now, you remember that I said that we are sending the synchro pulse to the vertical oscillator. Okay, so, and we're sending it through a capacitor and a potentiometer. And the reason why we do that is because you can't really start drawing before the negative pulse has been sent out. Okay? But you still need to get a cue when you are allowed to draw. So what do we need to do to be able to draw on time, so when we get the negative pulse, but not start to draw immediately when we get the pulse? Okay, so because we need to send out the negative pulse first, then we have to wait for, say, about 6 microseconds, and only then afterwards we can start to draw. Well, that's what this little circuit here does. It delays the negative pulse. The negative pulse comes into the capacitor, charges it up, and when it gets at a certain level, which, if you will read the specifications of a 555, is 1/3 of the voltage of the power you feed it. Yeah, when it reaches 1/3 of the power that feeds the 555, then the 555 starts to oscillate. And that's exactly what this little circuit does. It receives the negative pulse, delays it, and then sends it to pin 2. Remember? That's also a pin which is called a trigger pin, exactly for that reason. So yeah, there you have it. So we have a line generator, a vertical oscillator, which is a monostable oscillator, or sometimes it's also called a one-shot oscillator, and we have a horizontal oscillator. And since this one is perfectly synchronized with a line generator, we can freely generate any sort of horizontal frequency at which we want to generate our pattern, our vertical pattern, okay? Because this is always synchronized, it doesn't really matter what frequency, at what frequency we switch it on or off. When it's on, it will only draw when it gets a negative pulse from the line generator, okay, from this one. And that's it. And the signal that this one outputs, we mix in with this little attenuator together with the negative pulse, which we attenuate from the line generator. We mix both signals into this little attenuator and we output it to the video monitor. And ta-da! There you have it, your image generator. Now I know, it sounds a bit complicated, and it certainly sounds a little bit confusing, but I had to sort of bend my own mind around it, how that would work, but once you start building it and testing it, you quickly realize that there is no real reason to be confused, okay? So there you go. That's how we generate an image that we can output to a video monitor. Now, as a little encore, I also designed a small oscillator down here. This is one of my favorite designs, which is called a Colpitts oscillator. Now, a Colpitts oscillator is really a very simple, very stable oscillator, and you can generate pretty much any sort of frequency with it. I'm not going to explain it, okay? I made another episode which is called building a radio frequency IF generator, IF signal generator. I advise you to go and watch that episode. I explain in that video exactly how Colpitts oscillator functions. This one happens to output a frequency around 66 megahertz. Now if we want to test a TV set, let's say, which has an antenna input, then we can input our video signal we just generated here into our RF oscillator, this little circuit, and by amplitude modulating the high frequency signal, we can send our video signal as a TV signal to the TV's antenna. And that way we can test a TV in two ways. Either the TV has a video input and then you can use this output of the circuit, or the TV has TV signal input, okay, and then you can use this circuit or this circuit's output to output a signal to the antenna connector of the TV. And that's it. So here again you have the circuit I built. Now remember, I built this on a breadboard to quickly put it together, and that's what breadboards are good for. You can quickly throw together a few parts, connect them with some wires, and see if it works or not. Now the big disadvantage of this is that a breadboard is not an ideal circuit, okay? It's full of bad contacts and little wires. You can see a whole spaghetti of wires that can pick up all sorts of stray signals, noise in fact. So the signal I'll show you in a minute, which is generated by this whole circuit, is not too clean, but that's because all these wires here pick up all sorts of stray signals. Anyway, not everybody, not every one of us which is an electronics enthusiast has the luxury, like I have, to have an oscilloscope to watch a signal being generated by a circuit I designed. Okay, so some of you might not have an oscilloscope, so that's why I'm going to show you the signal this little circuit generates and outputs, and you see it over there. Okay, so you see two dotted vertical lines. The distance between those two lines is exactly 64 microseconds. Okay, now the signal that's being generated is synchronized exactly between those two lines, and on the left hand side, so on the below the left dotted line, you see the negative synchro pulse, the line pulse that's being sent out to the monitor. Okay, then you see a big fat line, a horizontal fat line at the top, then a tiny little spike back down, and then just right after it again a long fat line till the second vertical dotted line. Okay, now watch what this creates as image on the monitor. That's not totally unexpected. You see a dark gray field, a black line, and the rest of the dark gray field. Don't mind the flashing you see of the screen. That's simply an artifact because the shutter speed of the camera is not synchronized to the speed, the screen refresh rate of the monitor. Okay, so it has nothing to do with the pattern generator. Anyway, aside from some noise signals you see, so those little black lines, those jagged little lines you see all over the screen, that's noise being picked up by the generator. You see that the image is clear cut. You have one large dark gray field and one black line on the left hand side, and that's exactly what you see on the oscilloscope. You have a large wide dark gray field and a very thin black line on the left hand side of the image. Okay, and each pulse sequence like this, you see, is exactly one line of the frame. Okay, so if I show you, excuse me, so here for example you see, I'd say about 20 lines building up the frame. Okay, so, and you see it's a nice repetition of pulses one after the other. And if you put 625 of those, let's say, complex pulses one after the other, you build up an image. And that's exactly what we're doing. We're outputting, we're outputting 625 of these pulses, these composite pulses, towards the monitor, and that builds up an image like this. Okay, so it really isn't difficult to understand. Once you think about how the circuit is built and what the function of each oscillator is, then you can easily understand which part of the image is being generated by the line generator, which or oscillator rather, which part is being generated by the vertical oscillator and which by the horizontal one. So really it's not difficult to understand. So yeah, there you have it. And by playing, if that's the word to use, with the potentiometers, we can alter the image. Well, let me say, for example, let's say we want a wider line, okay, a line which is not thin like that, but a bit wider. Okay, well, watch what happens when I widen the signal on the oscillator, on the oscilloscope. Here we go. One moment, because it's a bit tiny here. No, I'm turning the wrong way. There you go. So it's barely perceptible, but you can see I'm increasing the width of the signal. Okay, the pulse is getting wider, and that's exactly what we want, of course. Hang on. There you go. See? Now we have a wide pulse at the bottom. Now watch what this does on the image. Now we have a wide black line. Now you say, hey, but the image has shifted. Yes, it has. Part of the reason for that is that, well, like I said, the circuit you see over there isn't exactly the stablest one, and it's quite jittery when I change the value of a potentiometer. So rather when I change the setting of a potentiometer. So unfortunately with that setup the image will jump around a bit over the screen. Okay, so instead of being drawn here, it shifted about a third of the screen to the right. But that's okay. It still shows you the principle of how an image is being built up. Okay? So there you go. That's, let's say in a nutshell, what a pattern generator does. Now, you can imagine that you can generate all sorts of patterns. I mean, this is only one pattern, but you can generate millions and millions of combinations of vertical and horizontal lines. So you can get all sorts of images if you wish. So let me just show you what happens when I play with the delay of the signal. See? So now I'm creating a black, a light gray, and a white line. Okay, this is the light gray, this is white, and this is black. And then you have a white line and then a black line again. So you can generate all sorts of patterns with this pattern generator. If you try a little bit, you can even generate squares with it, or rectangles, or horizontal lines if you prefer. You can generate any sort of combination of vertical and horizontal lines on a screen with this generator. And that's what makes it such a fun little pattern generator for testing monitors and TVs. Yeah, you can really generate any kind of image. Now, the more experienced among you will notice that the image is slightly bent here. Yeah, so you'll see that the image is concave. Excuse me. Well, yeah, concave from the white side or convex from the dark or light gray side. Okay, and that's because this screen here is pin cushioning, which means that on the left and the right of the screen the image bends towards the middle and then bends out again. So my guess is you can build a pattern generator, albeit a simple one, and of course black and white, for I'd say $3, $4, something like that. So that's really cheap. Okay, and it's really not difficult either to put together. So this is the nearly finished pattern generator. I did have quite a bit of work with the high frequency stage you see on the left, so that part right here, okay, to get it to work properly. And right off the bat I'm going to tell you, if you're going to build this pattern generator, you are going to have to sweat it out and do a lot of tweaking and tuning and calibrating to get it to work properly. But once you do get it to work properly, this is what you'll get on your TV screen. Okay, so never mind those flashing bands you see over there. That's simply the shutter of the camera, which isn't synchronized with the TV. But actually what you're seeing there is the actual TV signal I'm transmitting with my pattern generator. Okay, so that little thing over there. and that is giving this pattern, okay, which is really nice. And right away you see that the screen is pin cushioning. Yeah, you see that it has a deformation in the picture going towards the center, so it's curved in a bit. Yeah, and on this side as well, it's quite obvious here. Okay, so yeah, but okay, this TV is only used for testing purposes. Now if you're curious to see how the output signal at the antenna input of the TV looks like, well, that's it over there. Okay, so you see the signal is modulated, but it works perfectly. Okay, so what I'm getting now is channel 2 on my TV, and I don't know if you can see it, but channel 2 is right here. Okay, so okay, the guide is not really very accurate of the tuning knob, but it is channel 2. Okay, well, channel 2 here in Europe. I don't know where channel 2 would be in the States. In any case, that is it. Now you'll notice a few things that you probably hadn't seen before, and the 2 or 3 things most obvious are the little capacitor you see at the back over there, okay, and these 2 little coils. Actually, those coils are chokes, okay, and those chokes need to be there in the power lines or the power rail for the high frequency oscillator to work properly. Without those chokes and that little capacitor you see at the back, the oscillator would never work properly, because it seems the 555s you see on the right generate quite a bit of noise on the power rail, yeah, on the power lines if you prefer, and you really need to squelch those noisy signals on the DC line, and therefore you need to build in 2 of those little chokes. The one at the back, the little choke at the back, is one I had ready made. The other one you see at the front, so right next to the yellow wire, is self-made, okay, is homemade. It's just a little core I used of 3 millimeters diameter, a ferrite core, and I wound 20 gauge enamelled copper wire around it, and that gave me a little choke, pretty much the same one as you see at the back. Well, functionally speaking, it doesn't look as nice, of course, but it does exactly the same thing as the one at the back. Actually, it's just 13 turns of 20 gauge enamelled copper wire on a small ferrite core of 3 millimeters diameter. I'll draw your attention to that yellow and that green little wire on the front here. Okay. So what I did was I loosely coupled the video output with the signal input of the RF oscillator, and the reason for that is that I could have used yet another attenuator in between, so let's say a FET or transistor circuit, a tiny circuit, to attenuate the signal before I inject it into the RF oscillator. But that would be yet another part, and then it would just complicate further the circuitry. And you'll remember that one of my goals was to keep the circuitry really simple. Okay, and as it is already, it's not extremely complicated, but you still have quite a bit of work tuning it and tweaking and calibrating it. Okay, so no mistake here, it's cheap, it's relatively simple to make, but it's relatively hard to make it work properly. So yeah, I opted for a simple but effective solution for coupling the video part to the RF part on the left. Anyway, the result, as you can tell, is quite nice. Okay, so I opted, by the way, for this image because it gives me most information. I can see rolling if the TV rolls. I can see whether the image is distorted in the vertical or in the horizontal direction, and I can see whether the tuning works properly or not. So yeah, I opted for a sober, simple pattern on the screen. Now, if you prefer a different pattern, well, the only thing I would tell you is that you just need to play around with the settings of the pattern generator. So in essence, with all these variable resistors, okay, these potentiometers, they are multi-turn potentiometers, so just a few turns left or right will produce already, I don't know, 10, maybe 100 or 200 different patterns, just according to how much you will tweak those potentiometers. So yes, well, there you go. We have a pattern generator which now works as well on the video input of a TV as on the antenna input of it. So that's perfect, and it gives a useful pattern, at least that's what I think. Now, there are a couple of things left for me to explain, which is that, first of all, like I told you, it's possible you'll have to manufacture yourself a few little chokes, okay, like you're seeing in the picture. It's really not hard to do. You just wind tightly and neatly copper wire, enamelled copper wire, on a small ferrite core, and there you have it. You will have to manufacture yourself a small, let's say, signal transformer, which is built in my design by these two little loops of wire. The loops themselves are not electrically connected, okay? They are just very near to each other, and that's it. And on the screen you see the green wire is connected to the base of the high frequency oscillator. The yellow wire is connected to the video output, okay? So I'll need to make a little, well, let's say, transformer of my own to replace these two little breadboard wires. By the way, the whole thing is very, very sensitive to external noise and signals. Yeah, so let me show you what I mean. So you see the screen here. Okay, so now I'm going to bring my hand close to those little wires, the yellow and the green one. Watch the screen. You see? Although the result is funny in a sense, it's certainly not a thing that we would want to happen. So in that sense, to avoid that sort of noise, I will have to build in this little pattern generator into a small metal box, okay, which will provide adequate shielding. There you go. This is the finished design. The only thing I need to do is to mount it into a metal receptacle of some sort, and then mount a switch, an on-off switch, a power in connector, and two output connectors. I think I'm going to use B and C connectors for that. So there you have it, and you see the yellow and green component in the middle there. Well, that's my homemade coupling, you could say transformer. It's just two windings of 2 inches each of 22 gauge wire around a piece of rubber, insulation rubber, from an old round AC power cord, and that's perfect. And I glued it with cyanoacrylate glue, so super glue if you like, to the piece of rubber, and that's the end result. Okay, so just a couple of windings, one next to the other, and the yellow wire is connected to the video output, and the green wire is connected to the RF signal input. Okay, and they're just next to each other. Okay, and that's the result. So yes, I slightly changed the pattern. I like this one more, but you know, again, it's just a matter of taste. Okay, so if you prefer another kind of pattern, or maybe you think another pattern is more helpful to you, well, like I said, you can just set pretty much any kind of pattern you like. I mean, within limits, of course. You can only set a combination of vertical and horizontal features, but no round features. Now, should you ever manage to make a pattern generator based on my design, okay, and which is capable of producing, say, circular images, I would love to hear from you. So, but okay, the premise would be, of course, that you manage to do it with nearly exactly the same device. Okay, so no cheating. If you manage to do it with the components you see here, let me know. I'm curious. And this is the finished product. I mounted the print board into a nice little plastic box which I had lying about in one of my drawers, and I cut two copper panels, well, two small copper panels, which I used for bottom and top to shield any RF coming off the little device, and of course to shield against any noise from the outside. Now, it's not ideal, I admit that. It would have been better had I had an all metal box to put it in, but well, I don't have one, and but I still wanted a box to protect the device I built. One or two interesting details, perhaps. I mounted the switch which switches between RF and video in one corner of the device, as far away from the output, from the high frequency output of it, and I connected the normal video via a normal wire to one BNC connector, which I soldered also to the top cover, the copper plate. And I also soldered the negative, or the mass, of the other BNC connector to the copper plate, and the copper plate itself and the two connectors are soldered to ground of the device. The other interesting detail is that I connected the RF output of the device, which is down there next to that green little coil you see, via a you could say shielded cable to the BNC connector, and I connected the shielding of the wire to the top plate, okay, the copper plate, and thus to ground. Okay, so I think that's rather useful to have around it, okay, copper shielding or metal shielding, just to protect it from noise and to not have it radiate RF noise into the ether. Okay, so one last thing, I insulated the lower copper board, which you see through the box down there, okay. It's just a piece of copper I had laying around. I shielded that electrically from the bottom of the PCB with a piece of tape, okay, so that well, obviously there would be no shorts if the bottom of the PCB would ever touch the bottom of the case. So that's it.